For millennia, humanity has looked at the stars and asked the same rhetorical question: are we alone? For centuries, this was a question for philosophers, poets, and theologians. But the 21st century has brought an unprecedented paradigm shift. The question has moved from the metaphysical to the chemical. Today, we no longer look only for radio signals or alien megastructures. We look for molecules. We look for the invisible trail that life leaves in the light that passes through the vacuum. At the center of this revolution is the James Webb Space Telescope, a $10 billion sentinel positioned 1.5 million kilometers from Earth. Recently, its gold-plated mirrors were pointed at a tiny spot in the constellation Leo, focusing on a world that defies all our planetary categories. What it found was not an Earth 2.0, but something far more exotic and perhaps far more promising. For the first time, we have detected the chemical components of a global ocean and the possible signs of a gas that, on our planet, is produced exclusively by living beings. We are on the threshold of discovering that the galactic zoo is much stranger than we predicted, and that biology's next chapter may not be written on Earth, but in the hydrogen clouds of a world 120 light-years away. Astronomy has always been limited by our biology. Our eyes evolved to see visible light, a tiny fraction of the electromagnetic spectrum. For decades, the Hubble telescope gave us magnificent views of the cosmos, but it was largely a prisoner of the light we can see. James Webb changed the game by operating in the infrared spectrum. Why is this vital for the search for life? Because the molecules that make up an atmosphere, water, methane, carbon dioxide, leave their sharpest signatures precisely in the infrared. Imagine that every gas in the universe has a unique fingerprint. When starlight passes through a planet's atmosphere, these gases hijack specific colors of light. Webb works like a hyper-sophisticated prism, capable of breaking down this light and identifying exactly who was there to intercept it. Its primary target in this investigation was the exoplanet K2-18b. Orbitando a cool red dwarf star, this planet is not a solid rock like Earth, nor a gas giant like Jupiter. It belongs to a class of worlds that our solar system, for some mysterious reason, decided not to create: sub-Neptunes. The importance of K2-18b lies in the fact that it is located in its star's habitable zone, the region where temperatures theoretically allow for the existence of liquid water on the surface. However, being habitable is only the first step. Venus and Mars are also technically on the edges of our Sun's habitable zone, but they are hellish or frozen deserts. What makes Webb special is its ability to go beyond orbital position and analyze the chemical guts of the planet. By looking at K2-18b, Webb didn't just see a shadow passing in front of a star, it smelled a world that may be teeming with organic chemical activity. For a long time, the search for extraterrestrial life was Earth-centric. We looked for rocky planets with nitrogen and oxygen atmospheres orbiting sun-like stars. But the cosmos is creative. The discovery of K2-18b solidified a new and fascinating category of planets: Hycean worlds. The term, a portmanteau of hydrogen and ocean, describes planets that can be up to 10 times more massive than Earth, possessing dense, hydrogen-rich atmospheres and liquid water oceans that cover their entire surface. K2-18b is the prototype for this concept. With a mass 8.6 times that of Earth, it has overwhelming gravity that retains a thick layer of gas. On a planet like Neptune, this pressure is so great that water exists in exotic states, such as hot ice or supercritical fluids. But K2-18b seems to be in a delicate balance. Webb's analysis revealed an abundance of methane and carbon dioxide, accompanied by an almost total absence of ammonia. For astrobiologists, this silence of ammonia is a shout. In a hydrogen-rich world, ammonia should be abundant unless a liquid ocean existed to absorb and dissolve it. This hypothetical geology completely transforms our understanding of where life can emerge. Hycean worlds may have much broader habitable zones than rocky planets. Since hydrogen is an extremely efficient greenhouse gas, these planets could maintain liquid oceans even when very far from their stars. However, K2-18b presents us with a challenge. Beneath its oceanic crust, The pressure may be so intense that the water transforms into a layer of ice 7, a crystalline structure that does not exist naturally on Earth. Could it be possible for life to arise in an ocean that does not touch the rocky mantle, but rather a barrier of exotic ice? This is the frontier of astrobiology that Webb has forced us to cross. We are no longer searching only for a copy of our home, but for forms of existence that thrive under hydrogen skies and endless seas. To understand how the James Webb Space Telescope can see the chemical composition of a world more than 700 trillion miles, 1.1 quadrillion kilometers, away, we must realize that it does not look at the planet the way we look at a photograph. K2-18b is too small and too close to its star to be visually isolated by our current telescopes. For all intents and purposes, it is an invisible point drowned out by the glare of its host star. So, how do we know what is in its clouds? The answer lies in a masterful technique called transit spectroscopy. Imagine you are observing a giant spotlight from miles away. If a mosquito passes in front of that spotlight, you won't be able to see the mosquito, but you will see an almost imperceptible drop in the intensity of the light. Now, imagine that this mosquito is carrying a tiny soap bubble. When the spotlight's light passes through the transparent edges of the bubble, the color of the light changes subtly because the soap and the air inside it filter certain frequencies. This is exactly what Webb does. When K2-18b transits, meaning it passes between us and its red dwarf star, a tiny fraction of the starlight passes through the planet's atmosphere before reaching the telescope sensors. In that brief moment, the gases in the planet's atmosphere act as filters. Methane absorbs specific wavelengths in the infrared. Carbon dioxide absorbs others. Webb breaks this light down into a spectrum, like a high-precision rainbow, revealing valleys where light is missing. These valleys are the chemical fingerprints of the elements. In the case of K2-18b, Webb detected clear signatures of carbon, but what intrigued scientists most was what it did not find: ammonia. In a world so rich in hydrogen, basic chemistry dictates that ammonia should be ubiquitous. Its absence is powerful circumstantial evidence that a liquid water ocean exists beneath the atmosphere, scrubbing the ammonia from the sky by dissolving it. This technique transforms starlight into a barcode of life, allowing Webb to perform a chemical autopsy on a world we will never physically visit. If the detection of carbon and methane put K2-18b on the map, it was the possible detection of a much more obscure molecule that made astrobiologists' hearts race: dimethyl sulfide, or DMS. On Earth, if you go to the beach and smell that characteristic ocean scent, you are smelling DMS. This molecule is not produced by volcanoes, lightning, or simple mineral processes. On our planet, the only significant source of DMS is life, specifically, marine phytoplankton in our oceans. The detection of DMS on K2-18b, although it still requires definitive confirmation and further rounds of observation, is what we call a robust biosignature. Unlike methane, which can be generated by geological sources, such as hydrothermal vents, DMS is much harder to explain through abiotic processes. If the DMS signal is real, we would be facing the first chemical evidence of metabolism on another planet. Imagine the magnitude of that: a microscopic creature living in an alien ocean under a hydrogen atmosphere, emitting a gas that travels 120 years through the vacuum to be captured by a gold mirror at Lagrange point L2. However, science demands caution. The signal detected by Webb for DMS is weak and at the limit of the sensitivity of the NIR-SPEC and MIRI instruments. NASA and University of Cambridge researchers, led by astronomer Nikku Medhusudhan, were quick to warn that hints are not proofs. The atmosphere of a Hycean world is a chemical laboratory that we still do not fully understand. Could there be an unknown geological process on high-pressure planets that produces DMS without the need for biology? Perhaps. But the mere fact that we are discussing the presence of an organic marine byproduct on a planet outside our solar system is a milestone. K2-18b has gone from being an astronomical curiosity to the primary candidate for the greatest discovery in human history. We are looking at an ocean that may not just be water, but a biological broth in full swing.